Denise Mauzerall, a professor in the Woodrow Wilson School and Department of Civil and Environmental Engineering. And I say good pleasure, good fortune, because she really embodies so much of what I like about the STEP program. So Denise's interests center around the topic of air pollution and its links to a number of other issues such as human health, climate change, and agriculture. And she has a real knack for looking for, finding, for understanding potential win-win situations, situations where cutting down on one pollutant, a particular type of pollutant, then pays significant benefits in terms of some of these other issues related, say, to human health or climate change, and conversely, of course, spotting the lose-lose issues, the policies that not only create one problem but exacerbate other problems. And it's terribly important to know these sorts of things as one goes about developing realistic policy prescriptions. What I like about Denise's work, what I admire about it, is that it is wonderfully interdisciplinary, it's rigorous, and it's always policy relevant. And I'm delighted that she is joining us this afternoon to talk about potential air pollution, health, and climate implications of China's energy future. Denise Mauzerall.
Thanks, David, and greetings, everyone. It's a privilege for me to be up here talking rather than just introducing other speakers. I'd like to start by thanking various members of my group who have contributed a lot of the work I'm going to present today. Some of them are recent graduates like Wei Peng, who's now a postdoc at Harvard. Charles Li Yushin are both still PhD students here. Jun Yu is a visitor from Peking University who was in my group for about 6 months, a year and a half ago. Junin Yang, who's here now. Dan Westervelt, who was a postdoc and is now a research scientist at Columbia. So China has absolutely terrible air pollution. This was a particularly bad episode in 2013, but bad air pollution is a persistent situation in China, with people having small children going to hospitals to breathe filtered air, masks being worn commonly. This is a mask type I've actually seen a few people wearing. It's not just a caricature. And I was just in Beijing last month, and this is me with 3 Tsinghua professors getting ready to go out for dinner when the air quality was pushing what was about 400 micrograms per cubic meter PM 2.5. To put that concentration in perspective, here are measurements that were made at the U.S. Embassy in Beijing, starting in January of 2008 and continuing through the present, though what I think I have here is through the summer of 2015. What you see in blue are the actual measurements, 24-hour average measurements. What you see is the red line is the U.S. PM 2.5 standard of 35 micrograms per cubic meter, and the World Health Organization PM 2.5 standards of 25 micrograms per cubic meter, which is the level at which it's thought that there's very little to negligible health effects that result. As you can see, Beijing rarely gets to levels that low. In the United States, we rarely get to levels that high. So clearly, China suffers from terrible air pollution that it needs to address. Simultaneously, it is now the world's largest emitter of carbon dioxide. What you see here is a graph from 1960 through 2015 of CO2 emissions in gigatons of CO2 per year. In the early 2000s, China surpassed the European Union. In 2006, it surpassed the US as the largest emitter of CO2. And recently, and very excitingly, its CO2 emissions have begun to level off. Also, in a very promising fashion, the global total CO2 emissions each year have been about constant for the past 3 years, so 2014, 2015, and 2016, indicating that the world may be at a threshold of beginning to stabilize CO2 emissions. A challenge, of course, is countries like India, where the emissions are continuing to increase at an accelerating rate. And so what happens going forward will be very critical for climate. Putting this in a slightly different context, you can see in terms of per capita emissions, the US is still, of all the large countries, the largest emitters of the world, the largest per capita emitter. But our per capita emissions have been dropping, particularly in the last 10 years or so. The European Union's per capita emissions have been coming down. And China's per capita emissions have also, although rising rapidly since about 2000, have also begun to stabilize. So there is real potential in turning the corner on CO2 emissions. But we have a real challenge in simultaneously addressing air pollution and its associated health effects and successfully avoiding a 2 or 3 or higher temperature increase globally. What you see here is a canonical figure from the IPCC, which shows the radiative forcing, which is the amount of heat that the atmosphere traps, due to the change in concentrations of gases or aerosols in the atmosphere from pre-industrial to present time. And what you see is that carbon dioxide, oh, the cursor here is not showing very well. Yeah, so in the case of carbon dioxide, it's the largest forcer at about 1.5 or 1.7 watts per square meter increase in forcing since pre-industrial. Methane is the second largest, and you can see these other greenhouse gases here. But what I'd like to point out is that aerosols, which are those fine particles which cause health effects, have both a negative radiative forcing and a positive radiative forcing. This is black carbon, which has a positive radiative forcing, but many of these other aerosols, like sulfates and nitrates, which form the PM2.5 aerosols, in addition to the black carbon, have a negative radiative forcing. And they also are hydrophilic and act as cloud condensation nuclei and whiten clouds. And so the fact that we have high levels of air pollution has actually been like having an umbrella up, reflecting incoming solar radiation back to space, and hence keeping the climate cooler. As these air pollutants are removed, and their lifetimes are very short, so that if you stop emitting them in a week to a month, they're gone. Whereas these long-lived greenhouse gases are around for decades and centuries. So as we clean up our air pollution, we're going to be basically closing this umbrella that and revealing the full force of the positive radiative forcing of these long-lived gases. Now we've looked at this situation in some in a more rigorous way with Dan Westervelt and Larry Horowitz at GFDL when Dan was here as a postdoc, and what he did was he conducted simulations using the GFDL Global Coupled Chemistry Climate Model, using the 4 RCP scenarios as well as the historic emissions. And as you probably know, the RCP scenarios range from a modest scenario of 2.6 with warming that stays likely below 2 degrees Celsius to an RCP of 8.5, which has much higher warmings, perhaps as high as 5 or 6 degrees Celsius. And he did 2 sets of simulations for each of these RCPs. One was following the standard RCP, where the assumption is that the emissions of aerosols decrease over time, everywhere in total around the world. And another case where he held at 2005 levels the aerosol emissions constant. And what you see here is that in the case of all these RCPs, essentially in each case, the removal of aerosols results in about an additional 1 degree Celsius increase in global average temperature. So removing air pollutants thus means that there is likely to be an increase in global warming and hence an increased need to reduce the emissions of long-lived greenhouse gases more aggressively than would be necessary if air pollution levels remain constant. So emissions of aerosols are projected to decrease, but we wanted to also look at what was the effect of climate change on aerosols. So this is showing you the total aerosol optical depth, the aerosols in the column of the atmosphere, and as following each of the RCPs, and then in dashed lines again, the effect of holding aerosol emissions constant and just looking at the effect of climate change on the aerosol optical depth, the aerosol concentrations in the atmosphere. And climate change does result in some climate penalty. You can see that the aerosol optical depth in the RCP 8.5 does increase, but that's relatively modest increases compared to the large decreases resulting from decreased emissions. Okay, so we now have sort of the full spread of the issues of air pollutant emissions and their effect on climate and greenhouse gas emissions. But in the case of China, the effect of air pollution on health is extremely severe. The Global Burden of Disease study estimates that 1.6 million premature mortalities occurred in China in 2013 due to air pollution. And they've taken recent action in declaring a war on air pollution and have developed an action plan for controlling air pollution levels. The climate situation is a global issue. As I mentioned, China is the world's top carbon emitter, and they have made a commitment through their INDC to peak carbon emissions by 2030. And they've made an additional commitment that regardless of what the U.S. administration does regarding Paris and climate mitigation efforts, they will remain committed to their peaking by 2030, and they may certainly be peaking before that. So the details of their air pollution goal is to reduce PM 2.5 concentrations by up to 25% relative to 2012 levels by 2017, by next year. And as I mentioned, their peak greenhouse gas emissions on or before 2030, and as you saw, they seem to be stabilizing already at the moment. But a key question that few people have really thought carefully about, and that what we are really trying to do, is to think about how can these goals be achieved with maximum co-benefits. So there's overlapping and divergent strategies to address air pollution and climate change. Some are beneficial just for air pollution, others are beneficial just for climate, and then there's some which can address both. So addressing air pollution can be done quite effectively by reducing agricultural waste burning in the fields. You can often find in China or India fields that are being cleared by burning, and the smoke is, impenetrable. You can also scrub plants, power plant, industrial plants, and vehicle exhaust. That's something that's been done very successfully in the U.S. and Europe and other developed countries. And although it takes energy to run these pollution control devices, as you know, they're very successful at cleaning up our air. You can also reduce ammonia emissions from livestock and agriculture, which is important because ammonia is a precursor for the formation of secondary PM 2.5. All of those things are helpful, and probably all of them should be done in order to protect human health. But they don't really have a large effect on climate. Things that can be beneficial directly for climate change include capturing and storing carbon underground. There's a lot of work at Princeton that's being done on this. And unfortunately, it's not yet commercially available on a large scale. There's also efforts to reduce non-CO2 greenhouse gases, and that's actually something that's probably one of the most successful things the world has ever done to address climate change. Through the Montreal Protocol, which has phased out the production of chlorofluorocarbons, which destroy stratospheric ozone and which are very strong greenhouse gases themselves. And more recently, through an agreement to slowly phase out the production of hydrofluorocarbons, HFCs, which although they don't destroy ozone, are very strong greenhouse gases and were designed as substitutes for the chlorofluorocarbons. But I think that the key area for both, for co-benefits for air quality and climate, is this central green area, where you can reduce activities that cause pollution, and examples of this would be to reduce unnecessary steel production and substitute it with lower energy types of activities. increasing efficiency in anything you do, everything that's done, will reduce emissions of both air pollutants and greenhouse gases, and switching to clean fuels. And probably one of the more dramatic examples of this would be closing down a coal-fired power plant and substituting wind or solar power for that coal, and hence reducing the emissions of the air pollutants as well as the CO2. So the objectives of our recent work have been to evaluate potential co-benefits for air quality, health, and climate of various strategies in China's Air Pollution Control Action Plan and or plausible for implementation of China's 2030 climate plan. And we look at some things that are moderate and some things that are very ambitious for 2030. So I'm going to show you two sets of work, one focused on 2015 counterfactual cases, essentially, if such and such had been done today, this is what the benefit would have been. And another, the longer-term 2030 perspective. So the integrated assessment study design that we use is essentially to compare the benefits of the intervention compare the effect of an intervention to a base case. And so, like I said, we have present cases where we have a base case where we have standard emissions and we calculate the air pollution levels and the effects on health. And then emission reduction scenarios based on policies already in place or measures possible for immediate implementation. And then for the future, we do the same thing, except we project to the future, to 2030, business as usual, and look at various strategies with moderate or ambitious implementation levels. And so the integrated assessment approach is that we have the base case, and then we have a change in activity, which results in a change in emissions, and then we have a simulation using the base case and the changed case, and look at the change in PM 2.5 that results, and then we use dose response relationships to look at the change in mortality. And so a schematic of this is as follows. You can have a baseline emission inventory, and then we would substitute changes in emissions of reactive pollutants and greenhouse gases due to the intervention, and then we would simulate the air pollution over the region, and then we would model the changes in human exposure, and then we would model the changes in mortality that result from this. So sort of the whole integrated assessment flow. And for those of you who aren't atmospheric scientists, I just thought I'd put up a quick schematic of what a regional atmospheric chemistry transport model looks like, where you essentially have the world's atmosphere divided into grid boxes, or in this case, the region's atmosphere divided into grid boxes. Each grid box looks a bit like this one, where you have emissions into the grid box, you have chemical reactions occurring in the grid box driven by solar energy coming in, you have transport into the grid box, transport out of the grid box, and then deposition to the surface. And we run these models over time so we can see the evolution of the air pollution concentrations, and we run them over space so we can see the transport of pollutants from one location to another. So here is the results of a WRF-Chem model simulation. And then, of course, I always tell students, you can't believe a model until you can compare with observations. It's just pretty pictures unless you have some data to compare with. So we do extensive evaluations of the simulations with all the data we can lay our hands on. What you're looking at here is a simulation using WRF-Chem. This is PM 2.5. And you can see for January, April, July, and October, in the annual average, the distribution of pollution. The black dot is Beijing. And so you can see in winter, the North China Plain is highly polluted, with concentrations approaching 150 micrograms per cubic meter. Here you can see the comparison with the U.S. State Department's measurements in Beijing, and the model is doing very well, really, overall, in capturing the general trends of observations, with the exception that we do sometimes significantly underestimate the peak concentrations. So we then, as I mentioned, analyze the human health impacts of these changes in concentrations. And the way this is done is to use cohort studies that were conducted in the United States, where the concentrations that people were exposed to in different cities were tracked, and their health, the difference in the relative risk of premature mortality due to the different pollution levels was characterized you up to fairly low concentrations. And there was a recognition that in countries with pollution levels that were very high, that linear extrapolation of the effects wasn't quite right. And so this global burden of disease study took smokers and saw that they actually weren't all dead, even though they were exposed to enormous concentrations of fine particles. And so they made an attempt to make an extrapolation of how these curves should actually look. And for a place like China, and especially Beijing and the North China Plain that's so highly polluted, you can find that for diseases like stroke, you're sort of at this area where you can debate exactly what this curve should look like, but where it flattens out a little bit. So in super polluted regions, you actually have to move down fairly significantly in the pollution in order to start getting improvements in health. So we do these calculations to estimate the change in mortality due to the change in relative risk, due to the difference in concentration in the base case relative to the concentration in the scenario we're looking at. And so we look at the change in relative risk multiplied by the base case mortality multiplied by the population that's exposed in each grid box. So that's the basic outline of the approach that's used for most of what I'm going to tell you about next. Okay. So the first set of simulations for the near term are to look at the benefits of long-distance electricity transmission, modest sector-based scenarios for the power, industrial, residential, and transport sectors, and then the use of planned synthetic natural gas or natural gas to displace the use of solid fuels. This has a lot of details on it. I just want to highlight that the long-distance transmission simulations in the study were done by Wei Peng. The sectorial scenarios were done by her as well, and the synthetic natural gas and natural scenarios were done by Yu and Chin. And I will try and summarize the details of this as I go through. So looking at long-distance electricity transmission in China is actually building 12 long-distance transmission lines right now. And what you're seeing here are WRF-Chem simulations of annual average PM2.5 concentrations. You can see enormously high concentrations, of 70 to 80 micrograms per cubic meter in the areas that are red. And then what we did was looked at changes in the concentrations due to either substituting coal-fired power plants in the east that were really dirty and old with clean new ones, and we call that coal by rail, or substituting, and that's what you see here, the change in the east due to that substitution in SO2 emissions, or substituting those dirty coal-fired power plants, shutting them down basically, and replacing them with cleaner coal-fired power plants in the west and sending that electricity by the transmission line, which is largely what China is doing. Or shutting down those dirty coal-fired plants in the east and substituting them with 60% renewable electricity and 40% coal and sending them down those transmission lines again. And this is a summary of what I just told you, but you can see here the wind resource potential is greatest up in the north and the western part of China, and the solar radiation is largest up here in the north and then over Tibet. And so you can see the potential benefit of long-distance transmission for renewable energy because you could bring these resource-rich areas in to serve electricity to the more polluted eastern part of the country. So I'm now going to show you a series of graphs that look like this for a bunch of different interventions that I just mentioned. What you're looking at here is the change in CO2 on the top axis here due to the intervention, and the reduction in national total premature mortalities on this y-axis here. And what you can see is that coal by rail or coal by wire, basically closing down the dirty coal-fired power plants and bringing in clean electricity, have pretty similar effects on both health and, of course, on CO2, so you're doing basically the same thing. And if you can substitute renewable energy, electricity generation instead, you get a huge benefit for CO2 mitigation. And the same effect, essentially, a slightly larger benefits, but a small additional benefit for health because you're actually still adding some coal-fired power plant in the cleaner part of the country. Okay, so this then is the sectorial scenarios. And what was done in these sectorial scenarios, I'm sorry, I guess I do need to talk you through this for a moment. So there's the industrial scenario, the power, transport, and residential scenarios, and then the four of them combined together. And in each case, there's a 20% increase in the implementation of conventional air pollution control strategies. In the case of the industrial sector, there's also a 10% increase in energy efficiency, which according to the literature is extremely feasible. In the case of power, there's a displacement of 80% of the dirty coal-fired power plants with larger, cleaner ones. Transport replaced 80% of high polluters with average vehicle fleet emissions. And the residential sector replaced 20% of coal-based residential stoves with liquid petroleum gas. And what you see here is that the air pollution-related deaths are significant, but the industrial improvements are the largest. Residential improvements are second largest. But improving energy efficiency in the industrial sector swamps everything. It's hugely important for reducing carbon emissions. And secondly, that different strategies lead to different regional distributions of health benefits. And so you can see that cleaning up the residential sector has the largest benefits in the areas where these small coal stoves, which I'll show you in a few minutes, are widely used for heating as well as cooking. The industrial sector benefits across eastern China, the power sector also more widespread. And if we then look on the same figure at these benefits, you can see in blue that the benefits from the industrial sector really are the largest. And when you combine all of these benefits, all of these interventions together, you get the largest benefits for both premature mortalities and for CO2 mitigation. So there's a lot of things that can be done that have co-benefits for both. The last intervention I'd like to look at for the present scenarios is the use of synthetic natural gas. Now, China has plans to gasify coal to make SNG as part of its efforts to address air pollution problems. They have a lot of coal, they have very little conventional natural gas, but if you change coal to gas, it costs you a lot of energy to do that. And this is what their plans currently appear to look like. And you can see that potentially they will produce a lot of SNG. The 2020 target gas consumption is 400 billion cubic meters, and they are considering SNG production of over 200. But as of the moment, their production, their target is between 51 and 64 billion cubic meters. And so in these counterfactual scenarios that Yue-Chin has conducted, she used 57 billion cubic meters of synthetic natural gas. And if we look at these results, here you can see in brown, SNG, you can improve your health if you put that SNG into the residential sector, where combustion is very inefficient and people are exposed very intimately with the smoke that comes from these small solid fuel stoves. Improvements in health for the other two applications are very modest. But a key thing to notice is that you get the CO2 trade-off. You get some health benefits, but you get an increase in CO2 emissions as a result of using SNG. Alternatively, if they used natural gas instead of SNG, and they're signing contracts now with Russia to get conventional natural gas brought in by pipeline from Russia. They're also attempting to scale up shale unconventional natural gas production. If they use natural gas instead of SNG, they can get identical health benefits, but with a reduction in CO2 relative to using coal. So, future. And for the future, we looked at the use of solar photovoltaics at the 2030 national goal of 400 gigawatts. We looked at industrial energy efficiency improvements, what appears to be initially cost-effective and what's currently technically feasible. We looked at residential solid fuel use, and I'll show you some work that was done sort of on the side for this. And then we also looked at electrification, where we look at electrifying the residential and transport sectors either 30% or 50%, respectively, with 30% decarbonized electricity or 50% decarbonized electricity. We look at those benefits. So rather than having you look at this is the PV work was done by Jun and Yang, and then industrial energy efficiency by Wei and Wei for residential fuel use and electrification. So for photovoltaic production of electricity, there's two different ways in which it can be done. One is done at the provincial scale, where you essentially can't have renewable energy as your only electricity source at the moment because we don't have storage. Obviously the sun rises, the sun sets. You need to have something else that will fill in for the intermittency. And so in this PV provincial current form, we cap the penetration of solar at 30%, and we say it's only within one province. And you can see here that you can get a significant reduction in CO2 emissions and a modest improvement in health, even though this is only 400 gigawatts. Then if you have at the regional scale, at the regional grid scale, you can get a larger reduction in CO2 emissions because the intermittency can be smoothed out across the grid. And then I'm showing you here this figure because this is now going to be on the scale that we're going to look at the future for. And you'll see how electrification has incredible potential for really greatly reducing air pollution levels and CO2 emissions. But before we do that, I wanted to take a sidestep and show you some work that has been done by Charles Lee looking at the reduction of solar photovoltaic resource due to the air pollution in China. So because air pollution is severe, it blocks incoming solar radiation and reduces the generation of electricity that's possible. China has been developing its solar PV deployment at an exponential rate. And so in 2015, they were over 40 gigawatts. Their national target is 100 gigawatts, by 2020 and 400 gigawatts by 2030. But the severe air pollution has its impact on radiation. So here you can see the aerosol and aerosol optical depth in eastern China. So what we did to analyze the effect of this air pollution was to use a PV model that calculates the point of array irradiance incident on a solar panel. And so you can have a solar panel that's flat. You can have a solar panel that's angled to the south, so it intercepts as much of the solar radiation as possible given a fixed position. You can have a solar panel that tracks the sun from day to evening, or you can have a solar panel that tracks the sun from day to evening as well as tracking seasonally. And so you capture more of the radiation as you track it more carefully. And so we used surface irradiance data in order to get the direct and diffuse shortwave radiation from satellite data under three different atmospheric conditions. All sky, which means sky with clouds, aerosols, everything. Clear sky, sky without clouds, and then all skies without aerosols. And you can see that there's a significant reduction in point of array irradiance due to aerosols in the eastern part of China. And that decrease, the percent decrease on the provincial scale ranges quite significantly around the eastern part of the country. But the variation is smaller if you look at, these are the regional grids. So China has regional grids, and there's transmission around the grids. So you can imagine in a case like this particular grid that it would be possible to avoid having your solar panels put in a place where there's a lot of attenuation, have them further west and then transmit that electricity east. So aerosol impacts solar resources are significant in eastern China. They're significant enough that they actually compare with the effect of clouds. So here you can see this is the North China grid, East China, Central China grid, Northeast China grid, Northwest China grid, and South China grid. Depending on where you are, the effect of aerosols can come close to the effect of clouds, particularly in winter. And that's of importance because that's when your solar radiation is also the lowest. So aerosol impacts are higher in winter, comparable to clouds in northern and eastern China. And then finally, the question is, can you overcome some of this with more sophisticated tracking systems? And it appears, in fact, that the more sophisticated the tracking system, the more serious the aerosol effects are on reducing the radiation that they can utilize. So here's the point of array radiance due to aerosols, fixed at the optimal angle pointing south, with one axis tracking day to night, and two axis tracking seasonally. And the reason for this, it makes a lot of sense, is that the better you track the sun, the more your panel is going to be tracking a longer path through the atmosphere, and so there'll be more aerosols interfering with that solar radiation reaching that solar panel. So aerosol impacts are higher for tracking panels than for fixed panels. Okay, so the next scenario that we looked at was looking at the industrial sector, and here we have modest and ambitious interventions in terms of energy efficiency measures, and you can see here that you get mitigation in CO2 and mitigation in premature mortalities. Here you have the residential sector, and you get significant improvements in premature mortalities and modest change for CO2 by replacing 30% of residential coal-based stoves with natural gas versus 50% of residential coal-based stoves with natural gas. So let me just show you what these stoves actually look like. So this is a paper that came out earlier this year that was done by work by Jun Yu, who was in my group for 6 months, a while ago. And what you can see, these are the coal briquettes that are burned in residential stoves in China. These little stoves, they heat them up, and this is the smoke that comes out. And although you might think, well, this is just a small stove, and the effects probably individually aren't that large, the smoke does seep out of the homes, and it has a very large impact on the emissions, a very large contribution to the emissions of PM 2.5 and other fine particulate species like black carbon or organic carbon or precursors. So what you're seeing here is the annual emissions and emissions in January and February for Beijing and the two provinces nearby, Tianjin and Hebei. And this is based on an inventory that was put together at Tsinghua. And this is not our work. So all I'm showing you here is their estimate of the residential contribution in orange to the emissions in the winter particularly of PM 2.5, black carbon, and organic carbon. So you can see that in many cases it's over 50% of the emissions in these regions. And so this, we call this paper a major overlooked source of air pollution in the region. And there's now beginning to be increased attention placed on mitigating that source of pollution. What we did in this work was a similar approach where we had a base scenario and then we had two intervention scenarios. One where the residential emissions were removed from Beijing, and the other where the residential emissions were removed from Beijing, Tianjin, and Hebei. And we look at the change here in PM2.5 concentrations from these two scenarios. So in blue this is Beijing. This is the change in PM2.5 concentrations, and this is the concentration in the base case. And each of these dots represents a particular day over this 2-month period. So you can see that removing emissions from the residential emissions from Beijing improves Beijing's air quality, but removing them from Beijing, Tianjin, and Hubei really dramatically improves air quality within Beijing itself. This indicates not only that the residential sector is really important, but something that I think government officials in China are only beginning to recognize, which is that regional transport is really important in terms of controlling air pollution levels in Beijing. And you can't solve the Beijing air pollution problem simply by reducing emissions within the city. Likewise, in Tianjin and Hubei, removing the residential sector has a dramatic improvement in air quality for those two provinces. So one can say, okay, so, well, what we did was sort of this magical wand wave. We switched off, we removed the residential sector emissions. We actually also did 25, 50, 75% reductions and saw that the effect was fairly linear. But this idea of magically removing them isn't entirely far-fetched, because you could substitute liquid petroleum gas for the coal briquettes. And this is increasingly being done. It's a little bit expensive for very poor, but it's subsidized. Or you can also substitute electricity. Most homes in China receive electricity, and so electrification is an option where you would then reduce your emissions of air pollutants and also reduce your CO2 emissions associated with coal use. So, finally, I wanted to show you the effects of electrification. Because from our work, it looks like electrification has the largest benefits of anything that could be done in terms of co-benefits for air quality and CO2 mitigation. So what you see in this electrification scenario is to increase by 20% conventional air pollution controls in the power, transport, and residential sector. And then in the moderate case, to electrify 30% of vehicles and 30% of residential coal stoves using 30% non-fossil sources of electricity. And so you can see here that this is a dramatic improvement over any of these other scenarios. If you became more ambitious and they actually utilized 50% non-fossil sources of electricity and electrified 50% of vehicles and 50% of residential coal stoves, the improvements would be even more dramatic. And this idea of electrifying the vehicle sector may again sound a little far-fetched. In the United States, we don't see this happening very rapidly. China is a very different situation. In conversations with someone at NDRC who runs the Energy Research Institute modeling effort, Zhang Kejun, he was saying that in Beijing they now have they cap the number of vehicles they can sell. They sold in 2016 a quota of 60,000 electric vehicles, 90,000 conventional vehicles. They have an industrial policy now to build up the electric vehicle fleet in China in order to compete on the world market with electric vehicles. And they've strategically chosen to do that rather than going for hybrids because they don't want to compete head-on-head with Toyota in a world market. And so it's quite feasible that they're really going to move into the electric sector. And I think an important question is how much will non-fossil, non-coal-based electricity power that electrification effort? So finally, this is showing the benefits of combining all of these efforts together in terms of a moderate electrification and an ambitious electrification effort. So in conclusion, a variety of different interventions can all provide co-benefits for air quality and climate. And I think it's important not to think ever that there's a single silver bullet and not to dismiss things that seem small because they're small relative to other things, because collectively a whole suite of different efforts have to come to bear on solving these problems. PV generation is reduced by current air pollution. PV deployment will reduce emissions and increase generations with benefits for health and for climate across the board as it's implemented more widely. In the residential sector, there's huge opportunities for improving air quality. Our work in terms of premature mortalities only took account of the ambient air pollution. It didn't look at all at the indoor air pollution that the people who are using these stoves are exposed to. Kirk Smith at Berkeley spent his whole career looking at this and argues persuasively that those numbers swamp the ambient air pollution premature mortalities that result from the solid fuel use. And so there's huge opportunities to improve health by switching from solid fuels to either liquid fuels or electricity. And with decarbonized electricity, you will get huge benefits also for carbon mitigation. And then finally, electrification with decarbonized electricity provides the greatest opportunity to simultaneously improve air quality, reduce associated premature mortalities, and reduce CO2 emissions. And I think it's likely that China will really lead this effort. They seem to be focused on long-distance transmission lines, increasing penetration of renewable energy, capping their coal use, building their transport fleet with electric vehicles, and are increasingly open to the idea of electrifying the residential sector. So I think there's great potential for China to contribute to solving sort of air pollution and climate issues for not only its own country, but also more widely around the developing world. So with that, I'd like to thank my group members and key collaborators and funding sources.
Very much. We do have time for some questions if we could get the lights up. Well?
Yes,
So very interesting talk, thank you. Just one, you mentioned early on that China has a target of reducing its air pollution levels by 25% between 2012 and 2017, now that we're in 2016, and you know how far they are along. And the second is on the question of electrification of vehicles. I think there's another very interesting thing which is happening in China, which is electric bicycles, which I think is something which people haven't taken enough note of. But as a former student here, C.C. Guang, who's been doing some interesting work on that.
Yeah, thanks. That's a good point. So I don't know quantitatively how far along they are. There seems to be a general view that air pollution levels are improving, but I haven't analyzed the trends myself, and I haven't seen those trends analyzed. I mean, just anecdotally, the concentrations were nearly 400 micrograms per cubic meter when I was there last month, so they still have a long way to go. But they are very serious about it, and I think it'll take a little bit of time. There's an ambitious target.
Yeah, I had a question. You're proposing a lot of policies that I think most of them would be able to reduce the emissions by 2030, some of it significantly. In the Chinese NDC, one of the targets is just peaking emissions by 2030. So I guess that target kind of looks not really ambitious compared to what you're proposing right now. So I was wondering what are your thoughts about that?
Yeah, it's not ambitious. Peaking doesn't say where they're going to peak, right? So it could peak up here, it could peak here. So I think that they were hedging their bets. And I think making some commitment was such a huge step forward compared to being really recalcitrant about making any public statements that it was a big breakthrough to have an agreement first between the U.S. and China and then for them to come forward with an INTC. It looks very promising that they're going to exceed that target quite substantially. And I would expect that they'll come forward in future climate negotiations with more aggressive, ambitious targets. Perhaps that they're already fairly confident of meeting before they make those promises.
More technical question. I was wondering, you say you have to validate the model before you use it, and most of these findings are based on what can be run.
Yeah.
Did you only validate it at the Beijing site?
No.
In terms of, and the second one is, if you go to 2030, what do you use in terms of boundary conditions pollution coming in from, for example, India or Nepal, coming into the region, because, yeah, they go into your WRF model and go out and mix with the...
That's true. So for the boundary conditions, we're using Mozart. And I'm sorry, the first question was?
Yeah, did you validate it in more places?
Oh yeah, so we validated not only with Beijing, but also with the various US consulate measurements, and then with a larger network of measurements that the Chinese government are making that have been published in other peer-reviewed journals that are now posted on the web that we can use to evaluate. And you know, it's not perfect, but it's reasonably decent. So I mean, Beijing, you saw what it looked like, and models tend to underpredict peaks and overpredict minimum, but it's doing a reasonable job, and it gives us confidence since we're looking at differences that it's a plausible, you know, indication of the benefits of the interventions. Yeah.
Early on, you talked about displacing old coal power plants in the east with newer ones either in the east or the west, and you said that there wasn't much benefit for aggregate health or CO2 emissions from moving them to the west. Is that something that they're actually doing? And if so, why? And is it because it's less visible or less politically damaging to them to have deaths occurring out in the west? Or
So they're definitely doing it. I mean, there's an effort to shut down, bulldoze, eliminate the oldest, dirtiest coal-fired power plants that are inefficient and filthy. So that's happening, and then they need the power to come from someplace else. So they've been building them both in the east and also in the west with these long-distance transmission lines that they've built as part of their war on air pollution. Now, interestingly, China has had the reputation of building a new coal-fired power plant, you know, every week. They now have a moratorium on new power plants in 28 of the 32 provinces. So they're not building more coal-fired power plants at the moment. That may change, but at the moment they're not doing it. And it's an interesting question. Why did they do that? Because they weren't build those long-distance transmission lines before knowing whether or not the air quality benefits would be really substantial or not. They don't show that significantly in what I showed you, but in some locations, like in the North China Plain, it does have some benefits, and that's an area that's politically sensitive, and air pollution is terrible, and there's a lot of focus and attention on that region. Yes?
Do you have maps on population density, maybe to answer this question? Are there fewer people in the West or poorer people?
Yeah, well, I do have maps, but unfortunately not in this presentation. But you're absolutely right. Most of the population lives in the eastern part of China. The population density is particularly high if we go back to the beginning. So most of the population is, you know, around Beijing, Shanghai, and then there's high population also down in Guangzhou. But it's basically the whole eastern part of the country that has a high population. Yes, Rob.
So it was actually in your footsteps about 10 days ago. Some of the same Chinese you work with, though only a small number. Two comments. One, the word overcapacity was said over and over again. The reason they're not building more coal plants is they're not running the ones they have that many hours a year compared to what they intended to do. So they're catching, one could say they're catching their breath.
Mm-hmm.
Same thing is true of their wind and solar. It's not running in capacity. And they have an extremely irrational pricing system for electricity. They don't have marginal dispatch. So they're talking about copying us, but right now they have a plan to come to the coal plant must run 50% of the hours per year, no matter what else is going on. Rules like that they know are in the way of rationalizing. The other is the N-word, which you didn't use once,
N-word.
and which the Chinese often don't use either, but it's very much on their mind, and that's nuclear power.
I carefully use non-fossil.
I know you did, and they carefully use non-fossil, and it's very interesting that people are pussyfooting about this concept. They're planning to go 50 gigawatts of nuclear in the present period. They are building 50 gigawatts in the present period, which equivalent hours it's running at base load would be like close to the solar 400 gigawatts. Maybe not quite that much. The solar runs 1,500 hours a year. These things run 75. 100 hours a year perhaps, so you've got an enormous impact with the nuclear, and they're probably not done with it.
Yeah, they seem to be one of the only countries in the world that's still building nuclear. It's quite expensive, and as you point out, they have overcapacity, which in my conversations led to the idea of this increased electrification of the economy.
It plays right into the nuclear hand.
But it also plays into just using the capacity they've got right now, and then potentially deploying more of the renewables, which don't have the issues of renewables are cheaper than nuclear. They don't come with the proliferation issues. They don't come with the waste issues or the safety issues. And so, in my conversation, the focus seemed to be on pushing renewables and utilizing excess capacity and curtailing further the building of coal-fired power plants.
So it's slightly different people.
We should. That's it. Debrief.
Any other question?
A small question. You mentioned very briefly synthetic natural gas.
Yes.
And I don't know to what extent it played a role in your final materials here. But my recollection is that water was a big issue in production there. And I just wondered, you didn't mention what role it played subsequently. You just went through quickly. So, do you have any observations on the role of synthetic natural gas going forward?
It seems like it's not looking like it's going to go forward quite as much as they thought a couple of years ago. But Yuan Chin has actually spent the summer looking at the nexus for SNG of water and
and also working on your project, you also take the water cover and air quality interact nexus in the picture, which basically shows that synthetic natural gas has significantly water use from the upstream production side. For all other gas sources, like conventional natural gas or imported pipeline gas or even shale gas, imported gas of course not much fewer water use, but the shale gas also has much fewer gas source compared with synthetic natural. But when they are used in end-use sectors to substitute coal-fired power plants or to substitute coal in the industrial sector, they can actually reduce water usage. But for synthetic natural gas, still the upstream water consumption dominates the life cycle water use. And especially, just one more point is synthetic natural gas are mostly produced in Xinjiang and in the Mongolian areas, which are northwestern regions, which already have been the most the survey is the water scarce region.
Well, Denise, thank you so much for very
I know.